Everyone, this video is about area under the graph and the volume of solids of revolution. So if we're finding this shaded part um, right here, this shaded area here, we can just use the integral of the function from a to b. So the integral from a to b of f of x dx will give us this area. If the area is above the x-axis, this is above the x-axis, the value of this integral is positive. But if we want to find this area below the x-axis, we will get a negative value from this integration. And the value of area is always positive. So that's why the area is a negative the integral from a to b of f of x dx. So it's like minus something from here. In the end, it's positive. What if the area we want to find is this part plus this part here from a to c? So we're gonna have to split the integration from a to b, and this is above the x-axis, so we will get something positive from here. And the integral from b to c, this is below, so it's gotta be something negative, so we can use minus this. And the total area is therefore this something positive minus this, which is something negative. A common misconception is to use the integral from a to c without splitting the two integrations. And if we do this, what we get is the yellow area minus the brown area. So we're not adding these two areas, we're doing this area minus this area. So you can just use the above minus below the x-axis, or you can use absolute value all the time like this. In case you don't know what to do, it's always the absolute value of one integration plus the absolute value of the other integration, because we want this number to be positive, this number to be positive, and then we add everything. That's also possible. If we have two functions as the upper and lower boundaries, we can just subtract. It's from a to b, so in one integration, but we subtract the upper minus lower functions. Now, what if the area is bounded by the y-axis? So in this case, we use the integral with respect to y, dy here. So it's f of y dy. And notice that the limits of integration should be the smaller number and then the bigger number here. So the area to the right of the y-axis is something positive. We will get something positive from this integral and something negative from this integral. So we're gonna have to use negative this integral, which is something negative. So in the end, it's positive. Area is always positive. So for example, let's say we're finding the area of this, this shaded part here. The function is y equals x squared from 2 to 4. So the integral from 2 to 4 of x squared dx, the integral is x cubed over 3. We plug in 4, plug in 2, use a calculator, we get the area. Alternatively, you can also find the same area by finding the area of this big rectangle and this smaller rectangle. The area is therefore the big triangle 4 by 16. Yeah, this is not drawn to scale, 4 by 16, let's say. And this is 2 by 4. And we can just use the bigger rectangle minus this small rectangle minus this area. Now this blue shaded area is the integral from 4 to 16 of x dy. So the integral of f of y, so the integral of x dy, y equals x squared means x equals plus minus the square root of y. Positive square root of y means this part, and negative square root of y is the other half. So we're using the positive square root of y, which is the same as y to the power of 1/2. We integrate, we get y to the power of 3/2 divided by 3/2, so 2/3. Y to the power of 3/2, plug in 16, plug in 4, use a calculator, and we'll get exactly the same result. Volume of solids of revolution. So if we have this function and we find the area under the graph from A to B, we get this shaded area. If we rotate this shaded area with this x-axis as the pivot here, we are rotating this area with this x-axis as the axis of rotation, we will get this kind of volume. So it's like a cylinder, ugly cylinder. So the volume is pi, the integral from A to B of y squared dx. So it doesn't matter if the function is above or below the x-axis for this formula. And this is the same volume formula, but this is with respect to y, so x squared dy. If we have two functions, we do the outer minus the inner function. So we don't do upper minus lower, but we use the upper minus the lower. So we have here the volume when we rotate this area 360 degrees about the x-axis. So this is hollow inside here, and we do the outer radius or the outer function and minus the lower function. Yeah, it's like a roll of toilet paper. So for example, here, let's say we want to find this area, this volume here. So it's pi integral y squared dx, because with respect to x, y squared dx. The y is x plus 3, this is the function, a straight line. So x plus 3 all squared dx, which is x squared plus 6x plus 9. And we integrate x squared, we get this, 6x, we get this. Integrate 9, we get 9x. We plug in 4, plug in minus 3, and then we use a calculator and we get the final answer. Now alternatively, this is just a cone. We can just use the primary school formula, which is base area times height over 2. The base is a circle, so the area of a circle, the radius is, well, to find the radius, you see, this is when the x is 4, you plug in here, the y is 7. So actually this is 7, so the radius or this length here is 7. So the radius is 7, 1/3 pi r squared h. The h is from minus 3 to 4 is also 7. So radius is 7, the height is 7. We get exactly the same result. Alright, that's it. I'll see you again next time.